Another example here, I'm giving you a block diagram of a system, and where the input here is x of n, the output is taken from this point y of n, then we have a delay and we have a feedback from the output to the input again. Okay? And I'm asking you to calculate the impulse response h of n for this system and the step response, which you can call s of n for the same system. Of course, in order to calculate the impulse response, you need first to get the relation between the input and the output, which we call the difference equation, and then you substitute in this difference equation, you substitute with the input as impulse function, unit impulse function, delta n, right? If you want to obtain the step response, you should substitute the input to be unit step input, right? U of n. So let's start first by getting the relation. If the output is taken from here and this is a delay block, then the signal here will be y of n minus 1. This y of n minus 1 will be multiplied by a constant or amplified by a constant, so the signal here will be a multiplied by y of n minus 1. And then the output y of n, we can write the output y of n to be the summation of the input x of n plus a multiplied by y of n minus 1. So this is the difference equation that represents this system. And in general, as we said, that difference equation that represents any system, it can be a combination between yn minus 1, yn minus 2, in general, to any other delay, equals like a combination between xn minus 1, xn minus 2, and so on. We'll discuss this in the next video. However, for our example, we reach to this difference equation. If we want now to obtain the impulse response of the system, what we should do is we should replace x of n by delta of n, right? By a unit impulse function. In this case, the output will be equal to the impulse response, right? So we can say now that the impulse response equals delta n plus a h of n minus 1. Here, this equation, it's not a nice equation because we cannot find the closed form expression for the impulse response. However, we can, by tracking this equation, by observing what's happening with this equation, we'll be able to get an expression for h of n. How's that? Let's assume that the initial condition for our system, that our system is causal. Our initial condition was 0, which means that the output at negative 1 was 0. The output at negative 1 was 0. In this case, h of 0 here will be equal to delta 0 plus a h of negative 1. H of negative 1, by the way, it's the response of our system at negative 1, the output of our system at negative 1. And since we assume that initial conditions are 0 for our system, the output of our system is 0 before the input, because our input now is delta n, it appears at 0, right? So the output should be 0 unless there is an initial condition. So here we assume that all initial conditions, all the signals in our system before 0 was 0 or were 0, right? So now we assume that the response at negative 1 was 0. The initial condition was 0. And the response will start to appear after 0. So we assume here that our system is causal, basically. Okay? So here in this case, h of 0 will be delta 0. What is the value of delta 0? We said that delta, it appears only at 0. Delta 0 is 1, right? Plus a multiplied by 0. So h of 0 will be 1. Okay, let's move one step further. H of 1 will be equal to delta 1 plus a h of 1 minus 1, h of 0. H of 0 is 1, right? So it will be plus a. Delta 1 is 0. Delta, the delta function, at anything else other than 0, it's 0, right? So h of 1 will be a. Let's move one more step. H of 2. H of 2, substitute n equals 2, it will be equal to delta 2 plus a multiplied by h of 1. And h of 1 was h of 1 was a, right? h of 1 was a, so this will give you a squared. This is 0 again. What about h3? h3 will be equal to delta 3 plus a multiplied by h of 2. Delta 3 is 0. Always delta 3, delta 4, delta 5, delta of 6 will be 0. Why? Because the delta appears only at 0, right? It's 1 only at 0. At all other instances, it's 0, right? So delta 3, delta 4, delta 5, so in all the coming equations, all the deltas here, delta 4, delta 5, delta 6, will be zeros. And then we multiply a by the previous instant. A times the previous instant. The previous instant was a squared. So h of 3 here will be a times a squared will be a cubed. What do you expect h4 to be? It will be delta 4, which we said that it will be always 0, plus a multiplied by the previous instant. A multiplied by a cubed. So it will be a to the power 4. What about h5? It will be a to the power 5. h6, it will be a to the power, h of 6 will be a to the power 6, and so on. In general, h of n, if you keep doing this, you will find that h of n in general is a to the power n, but it starts from, we assume that it starts only from 0. Before 0, it was 0. So you can say it's a to the power n multiplied by un, right? Because here, why did we assume that it starts from 0? Because our input was delta. Delta appears at 0. So we assume that all signals before the input were 0. There is no signal in the system before the input comes, which means that our system is causal. We assume that our system is causal. All initial conditions, all the responses of our system before the input were 0. So we found here that our impulse response is a to the power n, a to the power n, un. If a is a fraction, a is less than 1, assume that a is less than 1, you'll find that here at 0, the response h of n will be a. Then at 1, it will be a squared. At 2, it will be a to the power 3, a to the power 4, and so on. This is what we call, before the 0, of course, was zeros. So this is our impulse response. This is what we call infinite impulse response. Infinite impulse response. IIR, infinite impulse response. Okay? So here our impulse response, it has infinite number of samples, infinite number of delta functions. Okay? So we call it infinite impulse response. So here we calculated that impulse response and we found it's a to the power n un. What happens if we want the step response? If we want to calculate the step response, all what we need to do is to go back to the convolution relation. Impulse response is the output when the input is, the step response is the output when the input is a unit step, right? So let's do that. The output y of n equals what? The output is a convolution between h and x. So we can write it as h of k, x of n minus k. From k equals negative infinity to infinity, right? This is the relation between the input and the output. If you want to calculate the step response, then you put x of n equals unit step. In this case, the output will be equal to the step response, right? So the step response will be summation from k equals negative infinity to infinity, h of k. And by the way, h of k, we found h of k to be what? We found h of k to be a to the power n un. Right? So it will be a to the power k, h of k, it will be a to the power k uk. Because h of n equals a to the power n un. So h of k will be a to the power k uk. And then x of n minus k will be u of n minus k. Now this summation, we have a to the power k multiplied by uk. This means that it will appear only for k's greater than or equal 0. So we can remove the unit step here, uk, and make that k starts from 0. And then this unit step, this is a unit step reflected. Be careful that the variable is k here, the variable is k. This unit step is reflected and shifted by n, right? So it goes from minus infinity to n. It will be 1 only from minus infinity to n. So this means that our summation will end at n. So the step response will be the summation of a to the power k from k equals 0 to n. We changed k from minus infinity to be 0 because of this unit step. This unit step, it's 1 only starting from 0. And this unit step is 1 only until n. That's why we changed the upper limit to n. And this is now our step response. If we assume that our a, let's take a number, 0.6 for example, then this will be summation of 0.6 to the power k from k equals 0 to n. This summation is it has a known closed form. It has a known closed form, and let me remind you of closed form of this summation of geometric series. So if you have summation of a to the power k from k equals 0 to infinity, this is 1 over 1 minus a. This can be written as 1 over 1 minus a. What if you have summation of a to the power k from k equals, let's say, n plus 1 to infinity? This summation, by the way, this summation is what? This summation is 1 plus a squared plus a cubed and so on, right? It can be written like this. This summation, it's a to the power n plus 1, a to the power n plus 2, and so on, right? What's the difference between this summation and this summation? This summation is exactly the same as this summation, but multiplied by a to the power n plus 1. That's why the closed form for this will be 1 over 1 minus a, but multiplied by a to the power n plus 1. So this summation can be written like this. This summation can be written like this. What about if you have a summation from k equals 0 to n? A to the power k. Isn't that the first summation minus the second summation? So this summation from 0 to n, it's like you are summing from 0 to infinity, and then you subtract the terms from n plus 1 to infinity, right? So this summation is the first summation minus the second summation. So you can write this summation as 1 minus a to the power n plus 1 over 1 minus a. So this summation now can be written as 1 minus 0.6 to the power n plus 1 divided by 1 minus 0.6, which can be also simplified as the step response can be simplified as 1 over 0.4 multiplied by 1 minus 0.6 to the power n plus 1. Okay, and 1 over 0.4, this is 2.5 multiplied by 1 minus 0.6 to the power n plus 1. And like this, we calculated the step response. One more thing to add about the previous example, where we calculated the step response to be the summation from k equals minus infinity to infinity, 0.6 to the power k, uk, un minus k, and then we said that uk is a unit step that starts from 0 upwards, and the other unit step is a unit step that goes from minus infinity up to n, Okay? And when we multiply these two unit steps, we will get only a multiplication between 0 and n. So the summation now, the summation due to the multiplication of these two unit steps, the summation can be written as summation from k equals 0 up to n 0.6 to the power k. However, the condition here, the condition for this summation to give you a value is that n must be greater than 0, right? In order to get some samples here to add, in order to get some samples to add inside the summation here, n must be greater than or equal 0. So this summation is only for n greater than or equal 0. We also found that a closed form expression for this summation to be 1 minus 0.6 to the power n plus 1 divided by 1 minus 0.6. But here, because this expression will be valid only for n is greater than or equal 0, to be mathematically correct, you have to multiply here by un to say that this summation exists only for n greater than or equal 0. You have to multiply by this unit step, right? Once you do that, you can calculate the step response at different values. So, for example, you can say that S1, S0, let's start with S0. S0 will be, you substitute 0 here, and here we reach to another form, 2.5 multiplied by 1 minus 0.6 to the power n plus 1 multiplied by un. So we can calculate S0, it will be 2.5 multiplied by, if you substitute 0 here, it will be 1 minus 0.6, so it will be 0.4, which will give you 1. Then you can calculate S1 by substituting in equals 1, it will be 2.5 multiplied by 1 minus 0.6 squared. And you get the value, and you can calculate S2 and so on. Okay, once you do you calculate the step response for different n's, then you can plot the step response as a function of n. So it's 1 here, then here it will be with any other value and so on. You can plot the step response. In general, we can say that the step response is the output when the input is a unit step function, right? So the output in this case will be the step response. So we can say, using the convolution relation, we can say that the step response equals summation of hk, and then we put the input as it was supposed to be x of n minus k. This is the convolution relation, but we are going to replace the input here with a unit step. So we are going to use here unit step of n minus k for k equals minus infinity to infinity. But because our unit step un minus k, it goes from minus infinity up to n only, then this summation can be written as summation from minus infinity to n h of k. So we found here that the step response will be the summation of the impulse response from minus infinity to n. Very similar to what we got in the continuous time signals and systems, is that the step response of a continuous time system, it was the integration of the impulse response from minus infinity to t. Here the step response is the summation of the impulse response from k equals minus infinity to n. Using this result, we can say also that since the step response at n is the summation from k equals minus infinity to n h of k, now let's define also s of n minus 1 to be summation from k equals minus infinity up to n minus 1 of h of k. Now let's subtract s of n minus s of n minus 1 What do we get if we subtract s of n minus s of n minus 1? These are exactly the same summations, except that here we have only one extra term, which is h of n, right? So you'll find that the impulse response h of n will be the difference between s of n minus s of n minus 1, the difference between the step response and the step response shifted to the right by 1. Okay? So this is a relation between the impulse response and the step response, very similar to what we got in the continuous time systems, except that here instead of integration we have a summation, and here instead of the differentiation in the continuous time systems we have a difference between s of n and s of n minus 1. We'll stop here in this video and we will see you in the next video.